So good morning. This lecture is supposed to be in English, but I don't know if the audience prefers French. I can switch to French, or one slide in English, one in French, if you prefer. English, okay. Okay, so since this is the first lecture today, I would like to introduce you to CERN briefly and to the Large Hadron Collider, and then I will focus on the main topic of my presentation, which has to do with the Higgs Boson, which, as you know, represents a very important step forward in fundamental knowledge and in our understanding of physics, fundamental physics, and also the structure and evolution of the universe. And I will also try to address the question, why is the Higgs boson important for our life? So first of all, I would like to remind you that CERN, this place, the European Laboratory for Particle Physics, is the largest laboratory in the world for particle physics. It's an excellent center where, over the last 50 years, scientists from all over the world have been doing fundamental research awarded by discoveries and Nobel Prizes. It's a center where the scientific goals require the development of cutting-edge technologies in a huge number of domains, and these technologies then are transferred to society. The most famous example is the World Wide Web, which, as you know, was introduced at CERN in the 90s to facilitate the information transfers among the scientists of the lab, and then it has changed the way society accesses information. But I will give you more examples later on, and we will also hear other examples in Erika's talk later on. It's also a center where we form people, tomorrow's scientists, but also school students and high school teachers through a huge number of activities and initiatives, and it's a fantastic place to bring the world together by attracting more than 10,000 scientists from 60 countries. So only one, I promise, only one historical and, say, political slide. So CERN was founded at the beginning of the 50s by 12 European states. And the goal was twofold, essentially. The first goal was to give back prestige to European research after World War II. And the second one was so this by creating a center of excellence. And the second one was to mitigate the conflicts of the Cold War, the Cold War that was already, the symptoms were already there. Today, CERN counts 20 member states plus some observers. So the member states are all from Europe. Then there are some observers from outside Europe, and there are also some associate countries that will become members later on. The budget is 1 billion Swiss francs per year. And is contributed by the member state, the 20 member states, in a way which is proportional to their pillar, to their how is it called? Budget. So this 1 billion Swiss francs corresponds, on average, to 1 cappuccino per European citizen. On average, because cappuccino is very cheap and very good in southern Europe, in Italy, and then when you move north, it becomes more expensive. And okay, fine. So this budget is used to pay the salaries of the around 2,000 CERN employees, CERN staff, and for the rest, it's used to develop the infrastructure, so the accelerators and the workshops and the various infrastructure that are used by the worldwide community to do research at CERN. And this worldwide community, as I mentioned before, consists of more than 10,000 users from 60 countries. And you can see here the map of the CERN, of the countries participating in a way or another as member states or observers or other kind of participation to CERN activities. Okay, so beside this sociological consideration, which nevertheless are important, and perhaps I will come back later on, CERN's primary mission is clearly science. So science means that what we are doing here, we study the elementary particles, for instance, among them the building blocks of matter, electrons and quarks, and the forces that control their behavior and their interactions at the most fundamental level. So I don't need to perhaps to repeat, because everybody knows today that matter, ordinary matter, is made of atoms. Atoms are made of electrons, so electrons are in turn made of a central nucleus surrounded by a cloud of electrons. The nuclei are not elementary particles. They are made in turn of protons and neutrons, and protons and neutrons are not elementary, meaning that they can be broken into smaller pieces and are made of quarks. As far as we know today, quarks and electrons are elementary particles. That is, they cannot be broken into smaller pieces, and they are the fundamental constituents of matter. So everything in this room, you, me, this table, and the microphone, the screen, everything is made of electrons and quarks, and a lot of empty space because the atom is essentially empty. Now, particle physics at modern accelerator, and the most powerful accelerator ever built is the Large Hadron Collider, allow us to study the fundamental laws of nature at this scale. This is at the scale of the quarks, which means below 10 to the minus 19 meter, which is smaller than 1 billionth of a billionth of a meter. So these accelerators can be considered as giant microscope that allows us to probe matter at this very small scale. At the same time, these studies allows us to give us insight about the structure and evolution of the universe. So if you want the very small, allow us to understand also the very big. I'm sure that you will learn more later from Licia talk, but the reason is the following. We know today that the universe had origin about 14 billion years ago from a big bang, from a big explosion. So at the beginning, it was very hot, and then it expanded and cooled down. And at the beginning, the universe can be considered as a gas of free elementary particles. And of course, with time, it cools down, and the particles start to stick together, first into neutrons and protons, and then in the atoms and of the lightest elements, hydrogen, helium, and then heavier elements, and then the microstructure that we know today, galaxies, planets, and so on and so forth. But at the beginning, as I said, the universe was a hot gas of elementary particles, so it was governed by the laws of elementary particles, and that's why by studying the elementary particles and their interaction, we can also have insight about the first instance of the universe life. So how do we do this in practice? What we do is to accelerate two beams of particles, for instance, two beams of protons, like in the LHC, at very high energy, speeds close to the speed of light, and then we make them collide. So the picture that I'm going to give you now is not a scientifically rigorous picture. It's very simplified, just to make you understand what we do. So please don't repeat it outside this room, because I will be fired. So let's keep it inside among us. So imagine these protons collide, they're accelerated, and then they collide. Okay, and you can imagine that they break into small pieces, and the higher the collision energy, the smaller the pieces in which they break. Like when you have two Ferraris, I don't know if you have ever driven a Ferrari, and of course at high energy, and then you smash them against each other, of course they go into thousands of pieces, and then you can understand how the protons are made, so you can understand how matter is made at the level of elementary constituents, the quarks. The second goal is that, of course, in the energy which is liberated from the energy which is produced in the collisions, new particles can materialize, can be created, because you know from Einstein equation, energy and matter are the same form, say, of the same quantity. So you have a lot of energy in the collision, and the collision can transform itself into particles. And the higher the energy of the collision, the more heavy the particles that you can produce. So particles that have not been observed until now at previous accelerators, because too heavy to be produced in the collision of their beams, become now available at the LHC thanks to the higher energy. And this is the example of the Higgs boson, which is not a heavy particle, it's quite light, but nevertheless it's produced in quite rarely, and so requires very high energy and very intense beams. And as I was telling before, the third goal is that in this high energy corresponds to the temperature that the universe had a few instants after the Big Bang. And actually, with the energy of the LHC, we are able to go back to a time which corresponds to 10 to the minus 11 seconds after the Big Bang, which means 100 of a billion of a second after the Big Bang. Okay. So we are able to understand what has happened until, back to that time. So this is what the accelerator and the collisions of the two beams produces. And now, then, to understand and to reconstruct the collision products, so the new particles that are produced and then decay, disintegrate, or the phenomena that have been that take place at the level of a collision, what we do, we surround the collision point with massive, high-tech, very complex instruments that are called particle detectors, which are used to ideally detect every single particle produced in the collision. Detect means measuring its energy, identify the particle, etc. So you will perhaps visit today some of these detectors. So we need essentially three things. Actually, we need four things. The first thing we need is human's brain, of course, to do all this. But then, from the point of view of instruments, we need three things. We need accelerators. Accelerators are usually rings in underground tunnels with a shape, ring shape. You will visit perhaps today the LHC tunnel. So here is a picture of the LHC tunnel. These blue tubes contain magnets, and accelerators are made essentially of two elements. Electric fields, which are used to accelerate the charged particles, the proton, for instance, incrementally at each ring, so at each incrementally at each turn. At each turn, the particles get a kink from an accelerating system, a radio frequency system. And, they are made also of second element, very strong, very intense magnetic fields, which are used to bend the particle and keep them inside the ring and to guide them into collisions. So as I mentioned before, this accelerator can be considered as a powerful giant microscope, which allows us to explore not cells or molecules, but the quarks. So go down to the very fundamental structure of matter. Then we need second element, we need detectors. So the collision between the two beams happens in the center of the detectors. The detector is an instrument which surrounds the collision point made of different technologies. And then all the products of the collision ideally are detected by this instrument. And you can reconstruct for the individual particles their trajectory, identify the particle, understand if it was a photon, an electron, or another particle. And then have a full view, a full picture of the collision event, and then at that point you can move to the interpretation phase and understand what kind of particles was produced in that collision, what kind of phenomena was at play. And finally, we need computers, a lot of computing power to store, distribute, and analyze the huge amount of data. I will give you some numbers later on, produced by the collisions and the detectors, and to reconstruct the collision event. Now, the most powerful and advanced and complex accelerator detectors and computers have been, of the history of particle physics, but I think more in general in the history of science, have been conceived, developed, and built in the framework of the Large Hadron Collider. The Large Hadron Collider has required innovative concepts and technologies in a huge amount of fields, from cryogenics, superconducting materials, electronics, data transfer and storage and treatment, etc., and the effort of the international collaboration for almost 30 years. Actually, the first discussion about a Hadron Collider at CERN happened in 1984, and the first collisions between proton beams occurred in November 2009. So you see a very, very long period. Since November 2009, we have been colliding beams. So the experiments have been recording data. This period has finished in February this year. So we had 3 years run, as we call it, data-taking period. And now we are in a period of shutdown. That's why you are able to go down and visit the cavern. Otherwise, you could not. In order to make some improvements to the accelerator and being able, in 2015, to move to even higher energy. So I said that we need 3 elements: accelerators, detectors, and computers. So let's start briefly with the accelerator. So the LHC is a 27-kilometer ring, 100 meters below ground, across the French and Swiss border. So we are here, essentially. We are more or less here. Okay. So here these little white dots indicate the border between Switzerland here and France. Lake Geneva is down here. This is Geneva Airport. Here you see the Jura Mountains. So, this ring here, this circle indicates the position of the location of the LHC, which is not visible on the surface. It's underground, 100 meters underground, and you see it extends over a very large area. Now, since November 2009, actually March 2010, we have been circulating beams at an unprecedented energy. In November 2009, the energy was not that high, but since March 2010, we have been circulating 2 beams in 2 opposite directions at an unprecedented energy. The collision energy was 8 TeV. I will tell you what this means. But just to give you an example, this energy is a factor of 4 larger than the energy of the previous most powerful collider, accelerator, and this was the Tevatron collider at Fermilab in the US. So these beams have been colliding in 4 main points indicated by these 4 stars, where 4 big underground caverns have been excavated, and 4 big experiments have been installed. And the experiments are called Atlas and CMS. These are the 2 biggest experiments, those who have reported the discovery of the Higgs boson, and 2 smaller but not less important experiments called LHCb and ALICE. I guess that some of you at least will visit at least one of these experiments. So I mentioned that the LHC is operating at an unprecedented energy. At the moment, the collision energy is 8 TeV, so 4 TeV per beam. So the total when the 2 beams collides is 8 TeV. And then in 2015, we will go up to 14 TeV. So what does TeV and what does this energy mean? Well, it's a lot of energy on the microscopic level, because 14 TeV corresponds to 100,000 billion times the temperature in this room. However, it's a very huge amount of energy on a microscopic scale. But on the macroscopic scale, this energy is nothing. It's just 1 microjoule, and 1 microjoule is the energy of a mosquito flying around this room. So from the point of view of macroscopic energy is nothing, but it's a lot of energy concentrated on a small point. Now, the single most challenging and the single most crucial element that has allowed us to gain a factor of 4 in energy compared to the previous collider is a set of about 1,200 superconducting magnets that are used to guide the beams inside the LHC tunnel. Because what is difficult in a proton-proton accelerator, unlike an electron-positron accelerator, is not to accelerate protons. Accelerating protons to high energy is quite easy, relatively easy. What is difficult is to keep these very high energy protons inside the ring and to guide them into collisions. Again, when you drive your Ferrari, if you are in a ring, in a racetrack which is a ring, of course, the higher the velocity of the Ferrari, the more difficult it is to keep the car inside the ring. And so what is difficult here is to have what limits the energy is actually the magnetic field that mankind can reach to keep these beams inside the ring. So it has required the development of high-tech, 1,200 high-tech superconducting magnets superconducting because only with superconducting material you can reach the very high current that are needed to reach very high magnetic field. Now, superconducting material work at low temperature, so these superconducting magnets, which are made of almost 8,000 kilometers of niobium titanium, which is a superconducting material, work at a very low temperature. The temperature is 1.9 Kelvin. 1.9 Kelvin means 1.9 degrees from the absolute zero minus 271 degrees Celsius. These magnets have been built by three leading European industry, Alstom in France, Ansaldo in Italy, and Babcock & Hörl in Germany. Second element, the detector, which have also required new concept and new technology. So this is ATLAS. This is an experiment in which I've been working for many years. It's actually the biggest of the four experiments. So it's 45 meters long, 25 meters high. And in order to have a better idea of the size, this is the size of two human beings, a man and a woman, because we promote equal opportunity in the experiment, so all our pictures contain a man and a woman. So you see the impressive size, and you will perhaps visit it. So why so big? So big because, of course, the particles produced in the collision are very high energy. So you need big volumes to absorb them and to measure them with high precision. You can't measure a very high energy particle in just 1 centimeter of detector. Okay? So you need big volumes for this reason. At the same time, because when the two beams collide, thousands of particles are produced in the collisions, then you need very high precision in the measurement of this particle and the capability of distinguish the individual particles. So you need something like 100 million individual sensors, mainly silicon sensors, in which the various elementary particles microscopically leave signals in the various elements so that you can track this thousands of particles with the precision of, say, typically few tens microns, where 1 micron is 1 millionth of a meter. So, for instance, this is an event recorded, a real event recorded by the CMS experiment. Not all the particles produced in the collision are shown, otherwise you will not see, it will be a completely messy picture, okay? But you can see the two beams interact from here to here. This is the interaction point, and you see the flow of particles out of the interaction, and you see that each individual particle lives in the sensitive elements of the detector, which are not shown here. You see some hits. Here you see some individual signal, and then by using software technique, pattern recognition, you can reconstruct the trajectories and have a full picture of the event. These red bars and blue bars are energies deposited by these particles in other detector elements called calorimeters. So these detectors can be seen as a very powerful, giant digital camera, which take pictures of the collision event, and then you reconstruct the results of this picture. However, these cameras have to be extremely fast because the two beams collide 40 million times per second. So this detector have to be extremely fast in order to be able to take this picture. Not all of the pictures are then stored, because otherwise we will not manage, not even with the most powerful computers, to analyze 40 million interactions per second. It's an enormous amount of data. Typically we store 200, 300 events per second, but nevertheless the detector have to be ready to record the event if the event is a good event, an interesting event. Also impressive is the size and the geographical spread of the community of scientists working in this experiment. So in ATLAS, 3,000 scientists, physicists, engineers, and technicians work from all over the world. You can see in yellow here the ATLAS map from South Africa to Australia to China, the US, etc., from about 38 countries. And most of these people are actually young. So, for instance, in this graph, you can see the age distribution of the ATLAS community, of the ATLAS population, in blue for boys and in red for girls. So, first of all, out of 3,000 scientists, about 1,000 are PhD students, and not to count then the young postdocs. So most of the collaboration is actually young. You see below 30, 35 years old. I'm here in the first bin, and I will not move out of that bin. I will don't laugh because it's not nice, not kind. Anyway, the other thing that you can notice is that women are at the level of typically 18–20%, but this fraction increases in the younger generation, which is a very good sign. So in the older generation, there are less women, but now we have many young women doing research in our field. Okay. In the interest of time, I will skip computing. Of course, I'll be very happy to answer questions, and then a few additional numbers in case you are not already impressed, to impress you more. So the proton beams, of course, travel at the speed of light, or close to it, and so they make something like 11,000 turns of the 27-kilometer ring per second. And as I mentioned before, they collide in the various experiments 40 million times per second. And when they collide, two beams through a system of magnets, quadrupole magnets, are squeezed in order to make them more intense and to increase the interaction probability. So their transfer size at the moment when they collide in Atlas, CMS, LHCb analysis, their transfer size is something like less than 20 micron, so much less than a human hair. So they are extremely small. I mentioned that the accelerator works at the magnets, superconducting magnets, work at 2 Kelvin. And actually, the LHC is the coldest place of the universe. It's not only cool, it's also the coolest place, it's also the coldest place of the universe, because the temperature of the universe today, we are in a phase of expansion of the universe, as I mentioned before, and the temperature today of the universe is 3 Kelvin. I think, I'm sure that Licha will tell you more about that, 3 Kelvin. But the LHC is at 2 Kelvin, 1.9 Kelvin, so we are colder than the universe. And actually, this accelerator can be seen as a bath of superfluid helium, 100 tons of superfluid helium, in which these superconducting magnets are immersed. These beams contain a lot of particles at very high energy. The protons travel at the speed of light, and when the machine is operating at the maximum power, there are something like 100,000 billions of protons circulating in one direction and the same number in the opposite direction. So the energy in these beams is very large, very huge, and therefore it's very important to control these beams very well, because of course if such a huge energy goes into a magnet of the accelerator, this of course can produce serious damage. So they are controlled at the micron level. If you want to know, so the energy stored in the beam when the LHC will operate at the maximum energy is 350 megajoule. If you want to know what this means, it's like the energy of a British aircraft carrier traveling at 12 knots. Now, why it has to be British, it's not clear, but okay, fine. This is what I found on the web. Say it must be British, cannot be American. Okay, so some other numbers. The CMS experiments contains more iron than the Tour Eiffel in Paris, and the weight is more than the Tour Eiffel, is 13,000 tons. Atlas is as big as half Notre Dame, again, to remain in Paris. In Atlas, we use 3,000 kilometers of cables to bring the signals from the underground cavern to the control room upstairs where these signals are stored, etc., etc. Computing. I didn't say much about computing, so let me tell you just one number. Every LHC experiment every year produces 10 petabytes of data, and this corresponds, if you wanted to write this 10 petabytes of data on DVDs, you will need a pile of stack 20 kilometers high. Okay, I hope that you are impressed enough, and so the next question is why? So why all this technological adventure and all this effort? So the reason is very simple. The elementary particles, like the electrons, the quarks, the photons, and many others, and their interactions are well known today thanks to more than 40 years of experimental, very meticulous and very bright experimental work, measurements, discoveries, performed at CERN and in other accelerators and in other experiments all over the world. These particles and their interactions are described by a theory which is called the Standard Model of particle interaction, and this theory is extremely successful because all the particles predicted by this theory have been discovered. Until the 4th of July 2012, one was missing, the Higgs boson, and now it has been found. So all the particles have been discovered. Not only, but also the predictions of these theories have been measured, for instance, here at CERN, with the previous machine, the LAP collider, which has been operating between 1989 and 2000. And the prediction of this theory, as I was saying, has been measured experimentally and with very high precision, and have been demonstrated to be correct. So we could be happy because we understand the world of particle physics, we have a theory, and we have very, very precise and complete observation. The problem is that the standard model, although it is correct, is not complete. It's not complete because there are a certain number of very important questions to which the standard model is not able to give an answer. So when we started to operate at the LHC, we didn't know, for instance, the origin of the particle masses, and this is now understood. We can tick it off. It's related to the Higgs boson, so I will come to this in a few minutes. But we don't know today, I'm sure that Licia will talk about this, what is the nature of the universe dark matter. Today we know only about 5% of the energy matter content of the universe, and the other 95% we don't know what's about. So we know that there is a form of matter called dark matter, which is about 23%, and then the rest is another mysterious form of energy called dark energy. When I say that we don't know what dark matter means that none, oh sorry, I should go back, sorry. None of these particles, or the standard model particle, has the right feature to explain dark matter as we have measured it with, for instance, astroparticle experiment, okay? So there is no candidate here for dark matter. So the standard model is not able to tell us, to give an explanation of dark matter. Dark energy is even worse. I leave this to Licia. We don't understand why there is a big asymmetry in the universe between matter and antimatter. There's very little antimatter, thanks goodness, otherwise we will not be here, and a lot of matter. So this we don't understand. Again, the standard model is not able to explain this imbalance. And we are not able, for instance, to understand how gravity, which we all know from common life, fits together with the other forces which affect the elementary particles. These are the electromagnetic force, the weak force, and the strong force, etc. So LHC has been built to address this question which, as I alluded to already, requires some physics beyond the standard model, because the standard model is not able to address them. So LHC has been actually built to find hints or possibly discover physics beyond the standard model. Okay, so the adventure started in March 2010 when, for the first time, LHC beam at high energy have been circulating in the accelerators, and first collision in that period inaugurated the exploration of a new energy frontier. So since then, the three fundamental elements of this enterprise, accelerator, detectors, and computers, have been performing extremely well beyond expectation. There has been a huge amount of collision. You can imagine we have been working actually until now 20 million collisions per second rather than 40 million, but okay, it's still a respectable number. And Atlas and CMS have each recorded 5 billion collision events. We have rediscovered all the particles of the standard model, so the list of particles you've seen before, we have observed them at the LHC again and measured them again in a new energy regime, and we didn't find any deviation, so the standard model is correct as far as we know, we knew already. And also we have been looking for physics beyond the standard model which could address at least some of the questions that I listed before, and for the moment we have found nothing. And so many of these scenarios have been ruled out, and of course in science, even a negative answer is a very good answer, of course, because it allows you to discard some of the possibility. But of course, most importantly, in July 2012, we have reported the observation of a new particle, which at that time we called Higgs-like, because it was
resembled very much to the Higgs boson, but at the time we were not sure. We were sure that it was a new particle, but its features were not yet well determined. And today we can see, we can say that indeed this particle is a Higgs boson. It's a particle that has a mass which corresponds to about 130 times the proton mass, so it's a quite heavy particle. So why is the Higgs boson so important? Because it addresses a question, it allows us to understand, gives us the answer to a question that has been with us for decades now. And the question is the following. We didn't understand until the 4th of July 2012, why some particles are, like the photon, are pure energy, no mass, and some other particles, like the electron, have a mass. We didn't understand why, for instance, the heaviest elementary particle observed so far, the top quark, which has been discovered at the Hadron Collider in the US in 1995, has a mass equivalent to a gold atom, whereas the electron is much, much lighter, 350,000 times smaller mass. The problem is that in the standard model, in this theory that describes so well the particle interaction, all the particles are massless. They are pure energy. But this, of course, contradicts experimental observation. We know that the electron has a mass. It has been measured. Okay? We know that the W and Z particles, which were discovered at CERN in the 80s and which are responsible for transmitting the weak force, which, for instance, govern radioactive decays or thermonuclear reaction in the sun, we know that these particles are massive, have a mass of 100 times the proton. So there was some problem in the standard model. So at the beginning of the 60s, a group of theorists, among which Professor Higgs from University of Edinburgh, introduced in the equations of the standard model, mathematical equation of the standard model, another piece, another part that allowed the photon to remain massless and the other particles to acquire a mass. The problem with this mechanism, called Higgs mechanism, was that as a result of this additional piece in the equation, the theory predicted the existence of another particle, which was called Higgs boson, which has been looked for 50 years and has not been found until last year. So I will try, before telling you why this particle is so important, I will try to explain you what we have understood in the evolution of the universe about the Higgs mechanism, in a very, very simplified way. And then perhaps Licia will tell you the more rigorous way. So what we know today is that, imagine, at the beginning of the universe, at the time of the Big Bang, all particles were massless, just energy, and they were going around in the universe, very happy, at the speed of light. No mass, speed of light. Okay? Imagine that already at that time, the universe was permeated with a medium that in physics we call a field. A medium, but this medium was essentially transparent. So the particles could not see it. It was there, like kind of ether, okay, transparent medium. The particles will go around, it was not visible. Then the temperature goes down because the universe expands and the temperature after the explosion goes down. And then at some point, and this point is 10 to the minus 11 seconds after the Big Bang, 100 of a billion of a second after the Big Bang, a transition phase occurs. And the medium, from transparent, becomes something more solid. Transition phase transition is a complicated term in physics just to indicate, for instance, when water becomes ice or vapor becomes water. The temperature goes down and the liquid becomes ice. Okay? Similarly here, this transparent medium becomes something more solid. At this point, particles start to realize there is something in the universe. Okay? And imagine that particles are like little balls. And imagine that the photon has a very smooth surface. And imagine that this medium is something like something disgusting, glue or molasses or jam. So if particles that have a smooth surface like the photon still go through the marmalade jam without seeing anything. But other particles, if the other particle has a rough surface, then of course they start to stick the glue and the marmalade, and they become fatter and fatter, and they are slowed down. So this, in a very, very pictorial way, of course, has nothing to do with the physics equation, explains a bit what happened. In the history of the universe, with the temperature going down, essentially, I say it now in a more rigorous way so that the physicists in the audience see that I know something, that the Higgs potential goes from an expectation value in the vacuum, which was 0 at the beginning, to something which is not 0, and this interaction between the Higgs potential and the particles gives the mass to the particles. Okay, wonderful. Why? I'm sure that, the problem was, as I mentioned before, that the Higgs boson had not been found. So this mechanism is wonderful, but nobody knew if it was true. The problem is that this was the best mechanism ever found. Okay, there were other ideas, but this was actually the solution that was really the most fashionable and the most compelling mechanism. And finally, we have found the Higgs boson. So I'm sure that I can anticipate a question from you. And the question is, who cares? Okay? And we should care about it, because the Higgs boson is a central piece for our life. That is, without Higgs boson, so if the elementary particle had not a mass, atoms could not stick together. The radius of the atom is 1 over the mass of the electron. If the mass of the electron is 0, because the electron has no mass, doesn't acquire a mass, then the radius becomes infinite. Atoms do not stick together. So atoms are, of course, the building blocks of ordinary matter. So we are what we are, and our universe is what it is, because the elementary particles have the masses they have, and exactly the masses they have. If the quark, the different species of quark, for instance, had slightly different masses, the proton could decay. If the proton decays, there is no hydrogen atom, there is no chemistry, there is no life. Okay? So the problem is that this key particle, for our existence and for the existence of the universe as it is, was not known until July 2012. We didn't know what was the mechanism, and today we know. So what did we observe in practice? Okay, so the theory, the standard model theory, predicts that the Higgs boson, once produced in these collisions, immediately decays. So it disintegrates immediately. For instance, in 2 photons. Photons are particles with very common, very familiar to our day-by-day life. This room is filled of photons. By the way, since the 4th of July of 2012, we know that the Higgs field came into play 10 to the minus 11 seconds after the Big Bang, and since then, it's here. This room is full of Higgs field. If there were no Higgs field, our electrons will not be massive, okay? So the vacuum is not empty. We know that the vacuum is not, on average, empty. The vacuum contains a field. And this field is the Higgs field. The terms of field is very now familiar to everyone through electromagnetic field, through, and etc. So in this enormous high-energy collision about the two, between the proton beams, we produce the Higgs boson, which disintegrates immediately into 2 photons. This is what the theory was predicting. So the 2 experiments, ATLAS and CMS, have looked at the recorded data. I told you 5 billion events today. In July, they were much less, but anyway. And we have looked, among the data that we have recorded, 2 collisions where 2 photons were produced. Okay, so for instance, this is one example of an event recorded by the CMS experiment. You see one proton beam from this side, the other proton beam here, they collide here. Several particles are produced, but among those, there are here 2 photons, and this green line represents the energy deposited by the photons in a detector, part of the CMS detector, in the part which is called calorimeter. So we take all the events that contains 2 photons, and we look at their spectrum. And we expect to see something like a smooth noise. And then if there is a new particles with a very specific mass that is produced, we expect to see a peak. And you can see here the peak by eye. This is the Higgs boson. This is the peak due to the production of Higgs boson that goes to gamma-gamma and to the photons. And if you subtract the noise, the background noise, then you see that the peak is even more evident. Likewise, we knew that the Higgs boson can, for instance, decay into 4 electrons. Again, electrons are particles that are very familiar in our day-by-day life. And so we have looked at the events containing electrons, and again, we observe a peak at the same mass as for the gamma-gamma decay. So this, again, is the kind of observation that we have made. Finding it, it was not easy at all, because this signal, the Higgs signal, is very tiny. The LHC produces 1 Higgs boson decay into 4 electrons every 10,000 billion proton-proton collision. So it's like looking for a needle in a haystack or a needle in many haystacks. So it required a huge amount of meticulous experimental work and a lot of ideas to be able to extract such a tiny signal from the huge background of other kind of proton collisions. Today, if you want to have an idea of many Higgs boson the 2 experiments have in their data sample, so out of the 5 billion recorded events, about 700 per experiment are due to the production of Higgs boson decaying in various different modes. So I will anticipate you the last 5 minutes trying to address 3 frequently asked questions. So the first question is this new particle the standard model Higgs boson? So this question has 2 kinds of answers. So first of all, since the 4th of July, we have recorded 3 times more data by the end of 2012, and with this data we have been able to measure the properties of this new particle in quite some details, and to demonstrate essentially the 2 fingerprints of the Higgs boson. Okay, I will not want to go into details, that it couples to other particles in a way proportional to masses, and the spin is 0. So, but anyway, this is a bit technical. So we have been able to demonstrate that this particle has the characteristics of the Higgs boson. However, we don't know yet if it is the Higgs boson predicted by the minimal theory or a Higgs boson belonging to a more general theory beyond the standard model, where there are more particles, more phenomena, perhaps additional Higgs boson. For the moment, we didn't find anything else, but of course, in 1 year from now, 1.5 years from now, we will move to higher energy and look for more. Of course, we would very much like the second solution, of course, that of course the Higgs boson is not standard, but there is something beyond it. Second question, is the task of the LHC over? And of course, the reply is no. No, because first of all, we have to make the full identikit of this particle, so to measure it in a more detailed way. This particle also, in turn, poses some questions. As always in research, you answer a question and new questions open up. But you remember, as I told at the beginning, as I said at the beginning, that the LHC has been built to address a huge number of questions: dark matter, unification of forces, gravity, etc., symmetry between matter and antimatter. And we have just ticked out the first question. So there are all the others to be addressed, and we have been addressing them in parallel. And the last question is, will the Higgs boson change our life? And so my answer to this question is that yes, and it did already, and it will do even more so in the future. And the reason is that in order to find the Higgs boson, we had to develop such a huge amount of new technologies and cutting-edge technologies in various fields. I mentioned these superconducting magnets that allow the proton beams to reach very high energy. I mentioned the instruments, the detectors. And these new technologies have been already transferred to society. For instance, in the world today, there are something like 30,000 accelerators, and more than half of them are used for medical application. I'm sure that Erika will tell you more details. Of course, they're not big as the LHC. They're perhaps a few meters long or something like that. But they've been, in any case, they've been developed based on the technologies that have been introduced and developed at CERN and in similar laboratories in particle physics all over the world. Likewise, we have developed instruments in particle detection to build our detectors that now are used in other fields, for instance, medical application like scanners, in medical imaging, etc. So in conclusion, at CERN, and in particular with the LHC, we are looking for answers to fundamental questions about the elementary particles and the structure and evolution of the universe. In order to achieve this goal, we have to advance the frontiers of technology, also to the benefit of society. Other missions of CERN are, of course, training the young people and bringing nations together. And I hope that I have convinced you that with the advent of the LHC, a new era of discovery has started with exploration of a new energy regime. And the observation of Higgs Boson represents a very important step forward in our understanding of fundamental physics and the building blocks of matter and the universe. I would like to finish with two remarks. I try to stress, and Erika will do so even more, the applications of what we do also for building instruments, for day-by-day life, medical application, etc. However, fundamental knowledge, research, justifies itself by the fact that it is the fuel of progress. I cannot tell you today if the Higgs boson itself will, this tiny particle, change our life. It's very difficult to predict. But every time you make a step forward in knowledge, this, sooner or later, brings you progress. When, at the end of the 19th century, a British physicist, Sir J.J. Thomson, observed for the first time a beam of electrons, thereby discovering the electrons using rudimental cathode ray tubes. The cathode ray tubes was the precursor of the television. In his laboratory, his life and the life of his neighbor didn't change. Could we today live without electrons, without electricity? So knowledge is clearly the fuel of progress. And also, I think that knowledge as art is one of the highest expression of the human beings as clever beings that distinguish us from animals. So should we say we don't support knowledge? We don't support art, for instance, because art is useless? So Picasso painting, why should I spend money in this thing? So clearly, it's very important that also do not forget this very important aspect. Okay, thank you. Thank you. So now we have a few minutes before the next presentation. Perhaps I can take a couple of questions and then give you a little bit of break so that you can catch your breath before Alicia starts. Yes, of course. Yes.
Let's say this is when they say in the beginning the ratio of antimatter and matter, the same that ratio between this proportion.
Yes. Yeah, okay, thank you for the question. So I try to clarify the matter-antimatter asymmetry. So as you say correctly, we think, because we are not there, that at the beginning, very close to the Big Bang, the universe was made of matter and antimatter in equal proportion. And then at some point, some asymmetry imbalance happened, and which favored matter over antimatter. This is nature's favoritism. And thanks goodness this happened because, as you know, matter and antimatter have a very unpleasant feature that they annihilate when they get into touch. An electron and positron together, they give just you some photons. So fortunately, otherwise we will not be here, okay? Now, the problem is the following, that in the standard model, in the theory that describes the elementary particles, it is possible to explain in part how this asymmetry happened. However, the standard model is not able to explain fully the phenomenon. In order to explain the asymmetry between matter and antimatter, you have to invoke a principle which is called CP violation. I don't go into details. The CP violation that is predicted by the standard model is far too weak to explain this huge imbalance. So what we are doing, in particular the dedicated LHCb experiment is doing, is measuring particle and antiparticles and try to find tiny differences to try to find different sources of CP violation, and so they could explain this matter-antimatter asymmetry. But again, this matter-antimatter asymmetry invokes new physics, because the standard model is not able to explain this phenomenon in such a big amplitude, okay? Just a part of it. I would like to perhaps mention something just to anticipate another question. People sometimes are scared about antimatter. Antimatter is nothing scary. It's not Dan Brown movie, etc. Antimatter, unfortunately, is very rare, but antimatter is something that is very common in our life. It does not, there is not much antimatter in the universe. The ratio between matter and antimatter is smaller than 10 to the minus 4. But at CERN, we produce antimatter every day. When you smash a beam of particles onto a target, you produce many particles, and you produce particle and antiparticle. The positron, which is the antiparticle of the electron, is the fundamental particle used in a medical scanner called the PET. Erika, you're going to talk about it, positron emission tomography. So you go to you see your doctor, and it makes a scan of your body, and the scan is made with positron, antimatter. Okay, so it's absolutely innocent thing, okay? Just to clarify. One more question, and then we switch to Licia. Yes, please.
What is your particular area of research?
My particular area of research, so I am an experimental physicist, so I'm not the kind of people who do calculation or theorists who introduced equation like Peter Higgs. I'm an experimental physicist, so what I do, I build detectors. So I've been involved right from the beginning of the LHC on the construction of a part of the Atlas detector, which is called calorimeter, which is actually used to measure the photons. So I was very proud that the detector on which I've been working for many years actually gave us very nice Higgs signal. So I build detectors, and also, I analyze the data, the results of this, this collision that have been registered, try to extract the interesting thing, doing measurements. Okay, I will stay around also later, so in case at the end, if you have other questions, of course, I will be happy to reply privately. And I now leave the floor to Licia, who will talk about